Hi, in this video, we are going to look at quadratic equations and we are going to solve a lot of problems in quadratic equations in this video. The point is to discuss all the types of problems that you may or may not have seen, but the techniques that you must know if you are preparing for JEE Advanced or for Maths Olympiads. So the topic is fairly straightforward, but the problems in the chapter could be quite tricky. Problems that you will encounter in this video will involve sometimes topics of number theory, sometimes algebraic identities, and lots of concepts. I would recommend that you try to solve each question yourself before you look at the solutions. And hopefully by the end of the session, we will have covered all the different types of questions you are ever likely to see in any exam. So I would assure you that like nothing new beyond these ideas you are likely to see in any exam that you write in the near future. So please pay attention to this video. Try all the questions in this video. There will be 20 plus questions and we are going to make a slightly longer session today and hopefully you will learn a lot from this one. So let's start with the first problem. This is question 1. It says let f of x be equal to ax squared minus bx plus c, where a, b, c are primes. A, b, c are primes. Given that the equation f of x is equal to 2023 has roots 0, alpha, beta, and gamma, with alpha plus beta plus gamma is equal to 26 by 43. We have to find ABC. Okay, so f of x is a quadratic and it is given that ABC, the coefficients are all prime numbers, and f of x is equal to 2023 has 4 roots. Obviously, it should have 4 roots because f of x will give us a 4th degree equation, right? And they have also given us that alpha plus beta plus gamma is 26 by 43, and you are supposed to find out the values of A, B, and C, right? Okay, so we'll start off by writing what is f of x. So this is a straightforward calculation. This is a times ax squared minus bx plus c whole square plus minus b times ax squared minus bx plus c plus c. And you have to evaluate this. When you evaluate this, it will come out to be like this. A cube x power 4 minus 2a square b x cube plus rx square plus sx plus ac square minus bc plus c, where r is a times 2ac plus b square minus b, and s is equal to b times b minus 2ac. How do I get all of this? It is just simple calculation and expansion. So you can check this out. This is going to be your final 4th degree function or polynomial. R and S I have written like this because it will make it too long. Okay? Now, obviously we can see from here that R and S are constants. These are depending on the values of A, B, and C, right? Now, Vieta's formulas, we know the roots of this 4th degree equation, right? The roots are 0, alpha, beta, and gamma. So from Vieta's formulas, we can say sum of the roots should be equal to negative of 2a squared b by a cube, right? And product of the roots you can see is clearly 0. So we get that this part is equal to 0. We are applying basic Vieta's relation and we get 0 plus alpha plus beta plus gamma is equal to 2a square b by a cube. And in the question itself, it was given that this was 26 by 43, alpha plus beta plus gamma. And you also have by the product of the roots, c times ac minus b plus 1 is equal to 0. Actually, I am making a mistake because the question had said that f of x was equal to 2023 had the roots 0, alpha, beta, gamma. So the actual constant term is going to be AC square minus BC plus C minus 2023, right? So C times AC minus B plus 1 is equal to 2023, right? This is what is coming by Vieta's formulas. So from here, it is obvious that you're getting B by A. B by A is equal to 13 by 43. And from here, we are getting this result, right? So we also know that A, B, and C are primes. If A, B, and C are primes, B by A is 13 by 43 implies that B is equal to 13 and A is equal to 43. It cannot be any multiple of that because if you put 26 by 86, for example, then B is 26 and A is 86, but it cannot be, but that is not a prime, right? You need to make A, B, and C primes. So when you take the ratio of two primes, you can directly say that the numerator is equal to 13 and A is equal to 42. And obviously, once you get this, you can easily put this value in this and get C times 43C minus 12 is equal to 2023. And basically from here, we can get the root C is equal to 7. So technically, this was a very straightforward problem. The whole thing was, can you expand f of x is equal to 2023? And can you use Vieta's relations in that? And take the sum of the roots, product of the roots, while keeping in mind that A, B, and C are prime numbers. If you take that into consideration, you will easily get this answer. Right? So that was the first one, pretty easy one. Let's go to the next question. Here, let A, B, and C be real positive and they are pairwise distinct. They are pairwise distinct. That means A is not equal to B, B is not equal to C, C is not equal to A, right? Let capital A be the set of all x belongs to real such that ax squared plus bx plus c equals 0. Capital B is the set of x belongs to real such that bx squared plus cx plus a equals 0. And capital C is the set of x belongs to real such that cx squared plus ax plus b is equal to 0. Now, we have to say that, prove that if A intersection B intersection C is not equal to null set, then A union B union C has exactly 4 elements. This is the question. First of all, you need to understand what the question means. So A, B, and C are positive reals. And what is this? The set capital A, capital B, capital C are the sets of real roots of these equations, right? The equations could have 2 real roots or 1 common real root or 0 real roots. A, B, and C, the sets are the sets of real roots for these 3 quadratic equations. The question is saying if A intersection B intersection C is not a null set, means all 3 sets should have some common element, right? That means all 3 equations should have some common real root, right? That is the meaning of this being not a null set. That means A intersection B intersection C has an element which is basically going to be the common root, common real root for all 3 equations, right? And then you have to show that the set of A union B union C is having 4 elements, right? So let's start by saying let R belonging to real be a common root, to all the equations, ax squared plus bx plus c equals 0, bx squared plus cx plus a equals 0, and cx squared plus ax plus b equals 0, right? Then obviously we will be able to write, let's write it on the next screen, ar squared plus br plus c equals 0, br squared plus cr plus a equals 0, cr squared plus ar plus b equals 0. This is true then. And if you add these three equations, you will get a plus b plus c common, and you will get r squared plus r plus 1 equals 0. And we know that a, b, c are positive real. A, b, and c belong to positive real. So this cannot be 0. So therefore r squared plus r plus 1 must be 0. And the roots of this, oh wait, r squared plus r plus 1 cannot be 0 because that is r plus half whole square plus 3 by 4. So this is greater than 0. So that must mean that a plus b plus c is equal to 0. So I have to check my assumption in the question. Was ABC right? A plus b plus c is equal to 0 is coming, right? Which means in the question they had said A, B, and C belonging to real numbers. Okay, I had misstated the question. If you go back, let's go back to the previous screen. This is not positive real. I had misstated this. It belongs to real numbers and they are pairwise distinct. Because if it is positive real, obviously the question doesn't work because a plus b plus c cannot be 0. Right? So what we have gotten so far is that if r belonging to r is a common root for all three equations, that implies that a plus b plus c is equal to 0. Okay? Great. And that means, look at the equations. The equations were like this: ax squared plus bx plus c is equal to 0, bx squared plus cx plus a is equal to 0, cx squared plus ax plus b is equal to 0. If a plus b plus c is 0, that it implies that r must be 1. 1 is a root for all three equations. Because you see, if you put x is equal to 1, you get a plus b plus c is 0, b plus c plus a is 0, and c plus a plus a is 0. Right? So therefore, what we know now is that 1 is a common root for all equations. So for the first equation, if you look at, the equation is ax squared plus bx plus c is 0. The roots are 1 and the other root must be c by a, right? 1 and c by a, because the product of the roots is clearly c by a. And what we can say here is c by a can be written as c by minus b minus c, right? Right. So the roots can be written as 1 comma c by a is equal to c by minus b plus c. These are the two roots for the first equation. For the second equation, the roots are 1 and a by b, which is equal to minus of b plus c by b. Because a plus b plus c is 0, a can be written as minus of b plus c. Just like because a plus b plus c is 0, a can be here written as minus b plus c. Correct. And the roots of the third equation in a similar manner will be 1 and third equation roots are 1 and b by c. And therefore, now we have to see what are the number of elements in A union B union C. Right? Right. So far we have the set A is 1 comma C by minus B plus C. the set B is 1 comma minus B plus C by B, and the set capital C is 1 comma B by C. Notice that we are writing it in terms of only variables of C and B, right? So what we have to figure out is how many elements does A union B union C have, right? So how many elements will that have? So basically we have to check whether some of these could be equal to each other or not, right? A union B, C, right? So if we have, if the root here is equal to this root, so basically if we have C by minus B plus C is equal to minus of B plus C by B, that would imply BC is equal to B plus C whole square, or B square plus BC plus C square is 0. But this is a contradiction. This is not possible because this can be written as B plus C by 2 whole square plus 3 square by 4, 3C square by 4, which is greater than 0. So these two cannot be equal, right? Correct. Similarly, if I try this is equal to this, let's see what happens if I say this is equal to this. So I will say C by minus B plus C is equal to B by C. I will get C square is equal to minus B square minus BC. And again I get B square plus C square plus BC is equal to 0, which is again a contradiction. It is not possible. So what I am able to say is that the second root here cannot be equal to this. This cannot be also equal to this. And similarly, you will get a contradiction between these two also. I will show you. So basically, minus of B plus C by B is equal to B by C. Let's try making them equal. Minus of B plus C by B is equal to B by C. And you get minus BC minus C square is equal to B square. And you end up with the same impossible situation. This is not possible. So none of these three are going to be equal to each other. So obviously, the number of elements in A union B union C will be 4, because you will have to list down 1 and you will list down all 3 of these unequal roots, right? So we have shown that the number of elements of A union B union C have to be 4, right? Because of the contradiction, if any of these are equal, there is a contradiction. So that is your second problem. Let's look at question number 3. Find the greatest negative integer n for which the equation x squared plus nx plus 2016 equals 0 has integer solutions. Okay. So we'll start by saying let R and S be roots of this equation. Roots of the equation. Now we have R plus S is equal to minus n, but we know that n is a negative integer. Minus n is therefore greater than 0. Right? So we have R plus S is basically greater than 0. And we also have RS is equal to 2016. Right? So RS is 2016. So both the integers have to be positive or both have to be negative, because their product is positive, and both cannot be negative because R plus S is greater than 0. So therefore R and S are positive integers that divide 2016. Why do they have to be positive integers? Because we have said that the equation is supposed to have integer solutions. It's not real numbers. We are talking about integer roots of this equation, right? So R and S are positive integers that divide 2016. So let's try to figure out, we have to find the greatest negative integer like this, right? So we have to basically try to minimize R plus S, because minimizing R plus S means we are minimizing negative n, has to be minimized. So basically we are maximizing, that means we are maximizing n. Maximizing n where n is a negative integer. So our job is to find the greatest negative integer, but R plus S was equal to minus n. So if I minimize this, I will get the minimum value of minus n, which will mean the maximum value of n, right? So that is what I'm trying to do. So let's try to minimize R plus S. So R plus S can be written as R plus 2016 by R, because RS is 2016. So therefore, by AMGM inequality, since both R and S are positive, we can apply AMGM. We can say R plus 2016 by R will be greater than equal to 2 times root of 2016, right? Now 2 times, the equality here will hold when R square is equal to 2016 or R is equal to root of 2016. That time it will be the equal to, so that will be the minimum value, right? Minimization in ANGM happens when both the quantities are equal, and therefore that time you will have the value of R is equal to root 2016. But root 16 is not an integer. If you calculate, that is equal to 44.89. So root 2016 is not an integer. So we have to find the closest integer to this which divides 2016, right? Because RS product is 2016. And R should be close to this for minimization, but it should also be a factor of 2016. So if you think about it and check some of the factors of 2016, you will realize R should be 42 and then S will be 48. Any integers close to 44.89, which both add up to 90, both add up to minus n, and product is 2016. Right? So this gives us R plus S is equal to minus n is equal to 90. So n is equal to minus 9. We are saying the greatest negative integer n is coming out to be minus 90 because these are the closest integers that minimize the value of R plus S and also are factors of 2016. Now, if you don't believe this, you can also check one thing. You can say, if n is greater than equal to minus 89, right? Let's see what happens. In that case, the quadratic x squared plus nx plus 2016 equals 0. The discriminant is n squared minus 4 times 2016. And in that case, the discriminant is going to be greater than equal to, n is greater than equal to minus 89. So n square will be greater than equal to, it will be 89 square minus 4 times 2016. So you will realize that this is actually negative, right? This is minus 143. So if you take, obviously if you take n is minus 88 or any smaller integer, any bigger integer, you will get even, that will be even more negative. Already at minus 89, determinant is negative, right? If determinant is negative, then this has no real solutions. So forget about integer solutions. You will not have any real solutions also if n is greater than equal to minus 89. How did we come to this number? We knew that n must be minus 90 because then only your R and S are basically 42 and 48, which are products of 42 times 48 was 2016, right? And R plus S was minus n, so that's how we got n was minus 90, right? How did we come up to 42 and 48? Because we were trying to minimize the value of R plus S. Keep R plus S as small as possible, which we did by ANGM. And from ANGM, we got that R must be close to root over 2060, which is 44.89. So then I look for nearby factors. So I hope you have understood this problem. Next one is this question. Question number 4. Let A is equal to root of R minus 1 plus root of 2R plus root of R plus 1, and B is equal to root of R minus 1 minus root of 2R plus root of R plus 1, where R is a real number greater than 1. Real number greater than 1. Given that A and B are roots of the quadratic, x square plus cx plus root over 2021 is equal to 0, find C. Okay. So A and B are the roots of the quadratic that is given, and A and B look very weird with radicals galore. So now what do we do here? Given that A and B are roots of the quadratic, obviously the first thing is to check Vieta's relation. So let's say that AB, the product of the roots, is going to be root over 2021. So let's find the product of the roots here. The product of the roots can be done in a straightforward manner by using the a square minus b square identity, and product of this and this will be root of r minus 1 plus root of r plus 1 whole square minus root of 2r whole square, which is equal to, the square of this is going to become basically r minus 1 plus r plus 1, so 2r plus twice of root of r square minus 1 minus 2r, right? So this gets cancelled, and you are getting product of the roots is twice of root of r square minus 1, right? Now apparently that should be equal to root of 2021. Basically we can say 2021 is equal to 4 times r square minus 1, right? So from here it follows that r square minus 1 is equal to 2021 by 4, and that implies that r is equal to 45 by 2. You need to add plus 4 by 4 to it, it becomes 2025 by 4, which is a perfect square, 45 by 2 whole square. So r is coming out to be this. R could also be negative 45 by 2, but the question had said that r is a real number greater than 1, right? Now, what is the sum of the roots? A plus b, sum of the roots is equal to minus c, and here the sum of the roots, if you see here, you will cancel the root 2r term and you will get twice of, basically c is equal to negative of a plus b, and if I do it on the next screen, c is equal to negative of a plus b, and that is equal to negative of twice of, this is root of r minus 1 plus root of r plus 1, but we have already found the value of r, so that is going to be root of 45 by 2 minus 1 plus root of 45 by 2 plus 1. So what we end up getting here is negative of 2, and this becomes 43 by 2, root 43 by root 2 plus this becomes root 47 by root 2. So if you simplify and take the 2 inside, you get negative of root over 86 plus root over 94, and that is the value of c, right? So we needed to find the value of c. The question is a really easy question. You just have to apply Vieta's relations, right? So that's it. That's the question. Let's move on to the next one. Is question number 5, and this says prove that for each integer a not equal to 0, 2, there is a non-zero integer b non-zero integer b such that ax squared minus a squared plus bx plus b equals 0 has integer roots. Basically, we have to show that for every integer a except 0 and 2, there is a non-zero integer b, such that this equation has integer roots. So, if I have to ensure that this integer has integer roots, so let's say x1 and x2 be the integer roots of this equation, right? Then from Vieta's relation, x1 plus x2 is equal to a squared plus b by a, and x1 x2 is equal to b by a, right? So a squared plus b by a plus b by a is x1 plus x2, and x1 x2 is b by a, right? So that means that we can write x1 plus x2 is equal to a plus b by a can be written as x1 x2. So now we can write it as x1 plus x2 minus x1 x2 is equal to a, and if I want to factorize this, I can do this x1 minus 1 plus x2 minus x1 x2 is equal to a minus 1, right? So we can easily factorize this. We can say x1 minus 1 common plus x2 1 minus x1 is equal to a minus 1, and factorizing this I can write it as 1 plus x2. Actually it will be a factor of, I will have to take negative of x2 here, so it will be 1 minus x2 x1 minus 1. 1 minus x2 into x1 minus 1 is equal to a minus 1, right? This is what we are getting. By using Vieta's relation and assuming that x1 and x2 are the integer roots, I am getting this condition, right? So let's see what are the solutions of this. If I have an equation like this, 1 minus x2 times x1 minus 1 is a minus 1. There are two cases. So one case is x1 minus 1 is 1 and 1 minus x2 is a minus 1, right? This gives us x1 is 2 and x2 is equal to 2 minus a, right? So in this case we have product of the roots is 2 into 2 minus a is equal to b by a. So we get b is equal to 2a into 2 minus a in this case, right? Correct. So for any integer a except 0 and 2, because for any integer a you can see b is 2a times 2 minus a, which is clearly going to be another integer, right? And since a is not equal to 0 and 2, b will be a non-zero integer. That's what I wanted to prove. B is a non-zero integer. So what did I do here? I started by saying that this equation has integer roots, and let's call those integer roots x1 and x2. By Vieta's relation, I got x1 plus x2 is a plus b by a, x1 x2 is b by a, and using those two we got this condition and finally this result. And since x1 and x2 and all are integers, this is the product of two integers which is equal to a minus 1. So obviously now you can take two cases. One of them is 1 and the other one is a minus 1. Or you can do the reverse also. x1 minus 1 could be a minus 1 and 1 minus x2 could be 1. But then in that case 1 minus x2 is 1 would give us x2 is 0, right? So if x2 is 0, that is a root, then b will be 0, right? So that second case is not allowed. I hope you follow why second case is not working on. If I say x1 minus 1 is a minus 1, 1 minus x2 is equal to 1, in that case x2 is 0. And if x2, which is a 0, is a root, then automatically the constant term of the quadratic must be 0. But we wanted to have a non-zero integer. So in that case, it won't work. But in the other case, we are getting the situation that the roots are coming as 2 and 2 minus a. And as long as a is not equal to 0 or 2, we get b is equal to 2a times 2 minus a, which is going to be a non-zero integer. So that finishes the proof of the problem. Right? Okay. Let's go on to the next one. Question number 6. Here we have to say find all pairs m comma n of non-zero integers such that m plus n is a root of the equation x square plus mx plus n equals 0. Find all pairs of non-zero integers mn such that m plus n is a root of this equation. So basically, if m plus n is a root, we can say m plus n whole square plus m times m plus n plus n equals 0. And if you expand it, you get m square here, m square here. So the overall equation will become 2m square plus 3mn plus n square plus n is equal to 0. And here m and n are non-zero integers. Right? And notice that this is a quadratic in M. Quadratic in M. So since M is an integer, the discriminant must be a perfect square. If a quadratic has an integer root, its discriminant must be a perfect square. So now we will evaluate the discriminant of this quadratic in M and say that that must be a perfect square. So what is the discriminant? We have 9n squared minus 4 into 2 into n squared plus n. So the discriminant is coming out to be n squared minus 8n. That must be a perfect square. So it must be some equal to q square where q is an integer. Basically, we are getting n square minus 8n is equal to q square where q is an integer. And we have to analyze that a little bit now. Square minus 8n is equal to q square. So from here we can say that n square minus 8n plus 16 is equal to q square plus 16. And this becomes n minus 4 whole square minus q square is equal to 16, which can be factorized like n minus 4 plus q, n minus 4 minus q is equal to 16. Right? Now the two factors here, n minus 4 minus q and n minus 4 plus q, both of them have to have the same parity. And by same parity means both of them have to have the same sign, because then only you get a plus 16. Can be have both negative or both positive, right? And obviously n minus 4 plus q will be greater than equal to n minus 4 minus q, because n and q are integers, right? So since these are integers and all, and both of them have the same sign, the only options for us are minus 8 and minus 2, minus 4 and minus 4, 4 and 4, and 2 and 8. These are the four options for these two factors of 16, right? Correct. Now, the first two are impossible because the sum of the factors here, if you add up the two factors here, you are getting sum of the factors in the first two case is twice of n minus 4. Twice of n minus 4 is going to be greater than minus of 8. We are getting twice of n minus 4. The sum here is coming out to be minus 8 or more, right? You're getting minus 10 and minus 8. Right. The sum of the factors should not be greater than minus 8. Or you can just check whether these two values are going to fit the conditions of the problem. If you take n minus 4 plus q as minus 8 and n minus 4 minus q as minus 2, you will be able to find, let's take it, n minus 4 plus q is minus 8, n minus 4 minus q is minus 2. So obviously if you add it, you are getting twice of n minus 4 is minus 5. N is equal to minus 1. And n is equal to minus 1. And if n is equal to minus 1, we can find m now, because you have 2m squared minus 3n is equal to 0. M can be 0 or n can be 3 by 2. But 3 by 2 is not an integer, so m is 0. You're getting m is 0, n is minus 1. But these are not non-zero integers. Remember, the question had stated that both m and n must be non-zero integers. These are not non-zero integers, so we have to reject this case. Similarly, when you take this case also, you will be able to see that it doesn't work, and these two cases are impossible. So basically, you have to work with the remaining two pairs. So we can say that both of them are 4 and 4. If both of them are 4 and 4, that implies that q must be 0, right? But you have n minus 4 plus q is 4, and n minus 4 minus q is also 4. So obviously if you add it, you get n minus 4 is 4, so n is equal to 8. So if n is equal to 8, you will get m value now. You have to look at the original equation and find the m value also. In that case, you will get m is minus 6. It's fairly straightforward to find m and n once you know these factors, right? So what you will end up getting is possible values of m and n are minus 6 and 8 or minus 6 and 9. And this corresponds to the factors 4 and 4, and this one corresponds to the factors 2 and 8. So you can check that these are the two pairs of values of m and n which work out, minus 6 and 8 and minus 6 and 9. When you have this situation, then m plus n, which is basically either a plus 2 or a plus 3, is a root of x squared plus mx plus n is equal to 0. If you think about it, x squared plus mx is going to be x squared minus 6x plus either 8 or x squared minus 6x plus 9. In this case, the roots are clearly going to fit. M plus n, 2 is a root of this equation, and 3 is a root of this equation. We have found the two different ordered pairs which work out, right? Okay, let's move on to the next problem. This is question 7. You have to find all pairs all pairs of AB of real numbers, AB of real numbers such that the roots of x squared plus ax minus b equals 0 and x squared plus bx minus a equals 0 are 1, 2, 3 and 5 in some order. So all the possible pairs A and B such that 1, 2, 3 and 5 are the roots of these two quadratics. So we will say let x1, x2 are roots of x squared plus ax minus b is 0 and let x3, x4 are roots of x squared plus bx minus a is 0, right? So from here we have x1 plus x2 is equal to minus a, x3 plus x4 is equal to minus b, x1, x2 is equal to minus b, and x3, x4 is equal to minus a, right? So clearly we can say that minus a plus minus b is equal to x1 plus x2 plus x3 plus x4, and that is basically the sum of all the four roots, and the question has said that the sum of the roots are basically 1, 2, 3 and 5 are the roots. So this must be 1 plus 2 plus 3 plus 5. So this is 11. So we have minus a plus minus b is 11. Basically a plus b is equal to minus 11 we are getting. And from the other condition, what is the product of the roots? Minus b times minus a. What is that? Now we'll use this result. So we'll get that is equal to x1, x2 times x3, x4. And that is simply 1 into 2 into 3 into 5. That is 30. So we get AB is equal to 30. So we are getting the conditions a plus b is equal to minus 11 and AB is equal to 30. So basically A and B are roots of x squared plus 11x plus 30 is 0. So basically A and B can be minus 6 minus 5, and they could also be minus 5 minus 6. This is the second order, right? Since it's an ordered pair, the order matters. So these are the two ordered pairs which satisfy the conditions of the problem, that 1, 2, 3 and 5 are the roots of these two quadratic equations. From the quadratic equations, basically we found out the sum of a plus b and also found the product of a and b. That gives us the value of a and b. Basically they can be minus 6 minus 5 or minus 5 minus 6. Right. Let's move to the next question now. This was question 7. So the next one, question number 8, is this question. Let a, b, c be non-zero integers such that the equation ax squared plus bx plus c equal to 0 has rational roots. You have to prove that b square is less than or equal to ac plus 1 whole square. So let's try to think about this. uh, if AC is greater than 0, then B square minus 4AC is clearly greater than 0. So therefore, B square minus 4AC could be written as equal to K square for some non-negative integer, for some non-negative integer K less than mod of B. See, if AC is greater than 0, B square minus 4AC is equal to K square. For some non-negative integer K less than mod B, think about this. APC be non-zero integers such that the equation has rational roots. Rational roots. The discriminant must be greater than or equal to 0, and the discriminant must also not be irrational. Because irrational roots will occur in pairs. See, we already know that the equation has rational roots. So this must be positive. This is correct. So the discriminant has to be positive to have rational roots, right? If it is positive, we can write it as equal to K square. Can we write it as equal to K square for some non-negative integer K? Right. Okay, correct. Why? Why is this? Because the roots are what? Roots are minus b plus minus root over b square minus 4ac by 2a, right? If it is not equal to K square, you will get a irrational term, but the roots are supposed to be rational. We are saying that it is a perfect square, basically, right? We are saying b square minus 4ac is equal to K square in that case, right? So then what we can say is b square minus 4ac is less than equal to mod of b minus 2 whole square, which was what? Mod of b square plus 4 minus 4 mod of b. So this is equal to b square minus 4 mod of b plus 4. Is this result true? B square minus 4ac, is it less than equal to this? So for this to be true, you have to have minus 4ac is less than equal to minus 4b plus 4, or ac less than equal to minus b plus 1, AC is greater than equal to B minus 1, or AC plus 1 is greater than equal to B is less than AC plus 1. Okay, so from here, it definitely follows that B is less than equal to AC plus 1. So we'll immediately be able to prove that B square is less than equal to AC plus 1 whole square. If we can show this, then it immediately comes from here that B square is less than equal to this, right? So we have to think about why B square minus 4AC is less than equal to mod B minus 2 whole square. We know that mod B minus 2 B square minus 4AC is equal to, we know it is K square. B square is less than, right, right. We have K is less than equal to mod B, right? If K is less than mod B, then K will be equal to at least less than equal to mod B minus 1. So 5 mod B minus 2. Okay. This problem is, we are getting stuck a little bit. I will think about this problem and we will revisit this problem. So let's hold off on this one. We'll revisit this question probably in a future video. Right now I'm getting stuck here, which is fine. Sometimes that happens. Let's go to another problem. Let's look at this one. Question number 8. Let A, B, C be positive integers such that B is greater than A square plus C square. We have to prove that roots of ax square plus bx plus c plus bx plus c equals 0 are real and irrational. Roots of this are real and irrational. Now, the question has said a, b, and c are positive integers. B is greater than a square plus c square. So obviously that a and c will, a square and c square will be greater than 1 plus 1 because they are positive integers. The lowest possible value of a square and c square will be 1 and 1. Therefore, we have b is greater than equal to 2, right? Correct. Also, that implies that b square is greater than equal to 2b because b is a positive integer. I can multiply both sides by b. And 2b is clearly greater than twice of a square plus c square. So what I am getting is that b square is greater than twice of a square plus c square. And by AMGN, I know that a square plus c square is greater than equal to 2ac. So from there, using that here, I'm getting b square is greater than 4 times ac. Because instead of a square c square, I'll write greater than equal to 2ac. So this implies that b square minus 4ac is greater than 0. Therefore, the roots of this quadratic are real. We have already proved one half of the question. Right? Now, we have to prove that the roots are also rational. Right? A, B, and C are positive integers ax square plus bx plus c equals 0, the roots are rational. We have to show. Now, the previous problem, which we did not completely solve, was set up in a similar way. There also a, b, and c were non-zero integers such that the equation ax square plus bx plus c was equal to 0. That equation had rational roots. And in that question, we were supposed to prove that b square is less than equal to ac plus 1 whole square for rational roots, right? So if you use the result from that question, we'll get b is less than equal to ac plus 1 for rational roots. So that means, what is b? We can say that two ac is less than equal to a square plus c square, and a square plus c square is less than b, is less than equal to ac plus 1. So from here, it follows that 2ac is less than equal to ac plus 1, right? That means ac is less than equal to 1. But that is not possible for positive integers. Not possible for positive integers a and c. So basically, what are we doing here? We are assuming that the roots are rational, and using the result of the previous problem, if you have rational roots for a quadratic ax square plus bx plus c, where a, b, c are positive integers, we have b squared must be less than equal to ac plus 1 whole square. This was a result that we have not yet proved, but we are going to use it here for the second question's proof. Because if b square is less than this, b is less than this, and now using a and gm here, 2ac is less than this, and we know a square plus c square is less than b, and again b is less than this. So we are getting 2ac is less than equal to ac plus 1, which means ac is less than equal to 1. Technically, there is a strict inequality here. See, we are getting 2ac is less than ac plus 1. No equality. But product of AC cannot be less than 1 because both of them are positive integers. The minimum value is 1. So that gives us a contradiction, which means that the roots cannot be rational. So they must be irrational. We have already established that the roots are real. We got this already. Now using the previous problem's result, we have also proved that the roots are irrational. Right? Let's go to the next problem. This says find all triples. Find all triples a, b, and c of positive integers such that the equation x square minus ax plus b, x square minus bx plus c equals 0, and x square minus cx plus a equals 0 have integer roots. Again, for integer roots, you will have to basically assume that, let's say, this equation has integer roots x1, x2. This has roots x3, x4. This has roots x5, x6. Let's say these are all integers, right? We have these conditions: x1 plus x2 is a, x3 plus x4 is b, x5 plus x6 is c. You also have x1, x2 is B, and x3, x4 is C. We have x5, x6 is A, right? Which basically implies that x1 plus x2 plus x3 plus x4 plus x5 plus x6 is equal to, basically see, if you add vertically these three, that is equal to A plus B plus C is also equal to x1, x2 plus x3, x4 plus x5, x6. Right. Now we can bring all the terms to one side and do the factorization technique here. Write it like this. How do I factorize this? What I have to do is add 3 on both sides and split it like I add 1 here, 1 here, 1 here, and add 3 there. So what I get is 1 plus x1 plus x2 minus x1, x2 plus 1 plus x3 plus x4 minus x3, x4 plus 1 plus x5 plus x6 minus x5, x6 is equal to 3, right? This can be factorized now because we can take x2 common here, the 1 minus x1. I don't have 1 minus x1, so I should do, perhaps I should have added minus 1. If I had added minus 1, what would I get? x2 common, 1 minus x1 and minus 1 minus x2, correct. So I should have added minus 1 on all sides. If I add minus 1, I'll get a minus 3, right? And eventually I will be able to factorize this, say 1 minus x1, x2 minus 1, right? Plus 1 minus x, similar terms here. Similar terms here is minus 3. If you simplify it and all, you will get this result at the end. x1 minus 1 into x2 minus 1 plus x3 minus 1 into x4 minus 1 plus x5 minus 1 to x6 minus 1 is equal to 3, right? Now, the question had said that the roots of these are going to be integer roots, right? Right. And all the triples A, B, C are supposed to be positive integers. So that means that each of these are going to be, see, if A, B, and C are positive integers, x1 plus x2 was A and x1, x2 was B. x1, x2 was B implies both x1 and x2 can be positive or both can be negative because B is positive. And if both are negative, you cannot get some of them is going to be positive. So both x1 and x2 are positive. Similarly, you can say x3 and x4 are positive, x5 and x6 are positive. So actually all of these roots are positive integer roots. So each of these xk minus 1 is greater than equal to 0. Therefore, what this means is that when you add this plus this plus this, all three of them have to be 1 and 1 and 1. The other option is it could be 3 and 0 or 0, 3, 0 or 0, 0, 3. So think about it. I will just write it here. All the xi's are positive integers. If they are positive integers, each of these factors is greater than equal to 0, right? So when you add These are all going to be positive integers. When you add three positive integers and it adds up to 3, there are only 4 cases, right? 111, that is case 1. The other case is 003, 030, and 300. These are the 4 cases in which we could add them and get a value of 3, right? Now, each of these cases we can try and evaluate if all of the things are 1. That means both of these integers are 1. In that case, all the xi's are equal to 2. If every xi is equal to 2, we get a is equal to b is equal to c is equal to 4. This is case 1. In the other two cases, for example, let's do this case 300, right? So then x1, x2, if this product is 3, you have to have 2 and 4 as the roots, right? Because then only you get 1 times 3 or 3 times 1. So x1 and x2 have to be 2, 4 in any order. And that means that a is equal to 6 and b is equal to 8. And now the other two polynomials have to have 1 as a root. 1 is a root in the other two polynomials, because then only if 1 is a root can this be 0 and this also be 0, right? And if 1 is a root, obviously the second polynomial, the equation for the second one was x square minus bx plus c, square minus bx plus c, and 1 is a root. So your 1 minus b plus c is equal to 0. C is equal to b minus 1. B is 8, so c is 7. So A, B, and C are coming out to be 6, 8, and 7 in this case. So case 4 we have solved, we got 6, 8, 7 here for A, B, and C. Case 1 we solved, we got A, B, C is 4. Similarly, you can solve case 2 also and case 3 also, and you will get these triples 8, 7, 6 for ABC here, and you will get 7, 6, 8 here. So technically your ABC can be either 4, 4, 4 or it can be different orderings of 6, 7, and 8. That is the solution for this one. Let's move on to the next problem. This question says solve the equation x power 4 minus 2m plus 1 x cube plus m minus 1 x square plus 2m square plus 1 times x plus m is equal to 0, where m is a real parameter. So m is a variable, it's a real number, and we have to solve this equation. So the point is to write this equation, you can write it as a quadratic in m. Right now it's a fourth degree equation when you take the variable x, but you can think about it and rewrite it in such a way that it can be written like this: 2x m square plus x power x square minus 2x cube plus 1 into m plus x power 4 minus x cube minus x square plus x is equal to 0. This is very useful. This is a very common technique. You have two parameters x and m. In x, it is a fourth degree equation. If you change the perspective and look at it from the point of view of the variable m, it becomes a quadratic equation in m. And now, since it's a quadratic in m and m is real, the discriminant of this quadratic must be greater than equal to 0. Right? And let's calculate the discriminant. The discriminant is actually x square minus 2x cube plus 1 negative of b. So this square minus 4 into 2x into x power 4 minus x cube minus x square plus x. Right? Now, b square minus 4ac. So this is what we are getting. Right, 8x here, and we can take x outside. So this becomes 8x squared, x cubed minus x squared minus x plus 1. Right? And this is x squared minus 2x cubed plus 1 whole square. Right. This is the discriminant of the equation. And you will have to simplify this discriminant a little bit. Right. Let's see what comes here. You get x power 4 plus 4x6 plus 1 minus 4x power 5 plus 2x squared minus 4x cubed minus 8x power 5 plus 8x power 4 plus 8x cubed minus 8x squared. So notice that you are getting x power 4 plus 8x power 4. You're getting 9x power 4 minus 4x power 5 minus 8x power 5. So you're getting minus 12x power 5. 4x power 6, and that's it. 4x power 6. And now x cube term, 8x cube and minus 4x cube. This is a plus 4x cube. And 2x square and minus 8x square. So minus 6x square and a plus 1. So this is what is coming as the discriminant. And let's think about that discriminant a little bit. I feel like it might be a perfect square. Let's see what is coming. So we can easily see, that these three terms are the square terms. So this is 2x cubed whole square plus 3x square whole square plus 1 square. Can we arrange it so that, okay, minus, we have minus 2 into 2, yeah, minus 2 into 2x cubed minus 3x square, 2x cubed into 3x square. This is going to give us a minus 12x power 5. Then we have a plus 2 into 2x cubed into 1 plus 4x cubed term. And I have a minus 2 into 3x squared into 1. Right? So this is clearly fitting the pattern. This is 2x cubed minus 3x squared plus 1 whole square. That is the discriminant. So after a little bit of algebra, we are getting that the discriminant of this quadratic is a perfect square. So now we are going to be easily able to find the roots of this quadratic. We say m is going to be equal to negative of x square minus 2x cubed plus 1 minus b plus minus square root of the discriminant, which was coming as out to be 2x cubed minus 3x squared plus 1 divided by c, which is divided by 2a. Right? So 2a is 4x. So let's take the two cases here. When we do plus sign, we get minus x squared plus 2x cubed minus 1 plus 2x cubed minus 3x squared plus 1 divided by 4x. So we basically get 4x cubed minus 4x squared, and this gets cancelled by 4x. So you get x squared, 4x common, this is x squared minus x. X squared minus x is the root when you take the positive sign. When you take the negative sign, you get minus x squared plus 2x cubed minus 1 minus 2x cubed plus 3x squared minus 1. This gets cancelled. You have 2x squared minus 2 divided by 4x. So basically 2 common, you have x square minus 1 by 2x. So you're getting two roots of n. M1 is x square minus x and M2 is x square minus 1 by 2x. Right? So basically, if x is not equal to 0, these are the two roots of n. So the initial equation was a quadratic in M, right? It was a quadratic in M which was written like this. This was my quadratic that I had started out with. I have found the roots of this quadratic. So the quadratic can be written as product of factors, right? So what I'm saying is I can rewrite this quadratic as a product of two factors, which is m minus x square plus x times m minus x square minus 1 by 2x, right? Basically equal to 0. We are getting m minus x square plus x times 2mx minus x square plus 1 equals 0, right? So now, since this is my equation, this is basically equivalent to the original equation. Now therefore, this will be 0. We have to solve the equation originally. This will be 0 if either of the two factors are 0. So we get two cases where each of these quadratic factors are 0. The first factor is 0 means x square minus x minus m is 0. And the solutions of this are, for x, solutions will be 1 plus minus root over 1 plus 4m by 2. And the second case is when we say the other factor is 0. Basically x square minus 2mx minus 1 is equal to 0. If the other factor is 0, you will get x square minus 2mx minus 1 is equal to 0. And in that case, the solutions are x3 comma 4 is equal to m plus minus root over 1 plus m square by the quadratic form. So I have gotten the solutions for x here and here. Remember the trick here. In x, the original equation was fourth degree. What we did was thought of it as a degree equation in m, which was a quadratic, and we simplified the quadratic, looked at its discriminant, and found the roots of the quadratic, basically found m in terms of x. When we found the roots of m, the roots were x square minus x and x square minus 1 by 2x. So we were able to rewrite the original equation in terms of product of two factors, m minus x square minus x and m minus x square minus 1 over 2x. So once you got that, that is equivalent to the original equation, and our point was to solve the original equation for x. So therefore now we took each of these individual factors as 0 and solved for x there. This is a very standard and very good technique that you must be aware of, because you might see this in different places. It looks difficult, but it is theoretically and conceptually quite straightforward. Okay, so this was, I think, problem number, just check. In the set of questions that we are discussing, this was question number 10. So we'll go to question 11 now. This is the problem that A is less than equal to B less than equal to C, be real numbers such that A plus B plus C is 0 and A square plus B square plus C square is equal to 1. You have to prove that B square is less than equal to 1 by 6. Okay. We have A plus B plus C is equal to 0 and A square plus B square plus C square is 1. So using A plus B plus C is equal to 0, can say that a plus c is equal to minus b. And let's try to also figure out what is AC. So AC is basically, you know that 4AC would be what? It would be a plus c whole square minus a minus c whole square. Or it could be written as also, you could also rewrite this as 2AC is equal to a plus c whole square minus a square plus c square. These are identities which give us AC. Let's not use the first one, let's use the second one. We get AC is equal to half of a plus c whole square minus a square plus c square. Right? So now AC is equal to half of a plus c is minus b, so this is b square minus b whole square minus a square plus c square is clearly 1 minus b square. Right? So this is becoming 2b square minus 1, and half of that, half of 2b square minus 1, that is b square minus half. Correct? We are getting AC product is b square minus half. And the sum of a plus c is minus b. Right? So if you think of a quadratic trinomial or quadratic function f of x, whose roots are a and c, the roots are a and c, so it should be looking like this. And now rewriting the values of a and c, you will get this polynomial looks like x square plus bx plus b square minus half. This is your f of x. This quadratic has roots a and c. Great. Now think about it. If the roots are a and c and the quadratic looks like this, the graph of the quadratic will be like this, right? A is a root, c is a root, but you know that b lies between a and c. B is somewhere here, so f of b is less than 0. Because it's an upward facing parabola here, and f of b must be less than 0. So if you put f of b is less than 0 here, what we get is b square plus b square plus b square minus half is less than 0. Right? Less than equal to 0. Which basically gives us 3b square is less than equal to half. Basically proves that b square is less than equal to 1 by 6. This is a very nice problem. Here, there was no mention of a quadratic equation in the beginning. They just gave us a plus b plus c is 0 and a square plus b square plus c square is 1. And this inequality on a, b and c. They wanted us to show this. What we did was we converted it into a quadratic problem by looking at what is a plus c and what is ac. Product of roots and sum of roots. And we made a new function f of x which has roots a and c. We found product of roots a plus c is minus b, sum of roots is minus b, and product of the roots is b square minus half. That comes from this identity. Once we got this, we were able to look at this function and say that its roots are a and c. And since b lies inside the roots, f of b is less than equal to 0, and that finishes the problem. Let's look at the next one. It says, let a, b, and c be non-zero complex numbers and let z0 be a root, z0 be a root of the equation az square plus bz plus c equals 0. We have to prove that mod z0 is less than mod of b by a plus mod of c by b. Okay. So let's think about this. A z0 square plus b z0 plus c is 0. A z0 square plus b z0 plus c is equal to 0. So since this is a solution of this rule, because this equation, So if I try to isolate Z0 from here, what I can say is A Z0 square is minus B Z0 minus C. In dividing by A Z0, I get Z0 is equal to minus B Z0 by A Z0 minus C by A Z0. Right? You're getting Z0 is equal to minus B by A minus C by A Z0. You're getting this relation. Correct? Now, let's take two cases in which we want to prove this, right? Case 1 is mod of Z0 is less than equal to mod of B by A. If mod of Z0 is less than equal to mod of B by A, obviously this is obvious that mod of Z0 will be less than mod of B by A plus mod of C by A. Because it's already less than this, so it will be less than something larger. So it is obvious in this case. We are going to work in case 2 where mod of Z0 is greater than mod of B by A. Right? We are working in this case because case 1 is trivial. Now, looking at this result here, I can take modulus on both sides and say modulus of Z0 is equal to modulus of minus B by A minus C by A Z0, and applying triangles inequality, I'll say mod of Z0 is less than equal to mod of minus B by A plus mod of minus C by A Z0. Right? Now think about it. This is same as mod of B by A plus mod of C by A Z0. But we know mod of Z0 is greater than B by A. Right? So replacing mod of Z0 here with a greater value, with a smaller value of B by A, we'll be able to say mod of Z0 is less than mod of B by A plus mod of C by A and B by A. So this becomes mod of C by B. Instead of Z0, I have put a smaller value of B by A. That still satisfies this inequality, right? Because if I put a smaller value in the denominator, it will be lesser than the overall thing. So you are able to establish this inequality in a pretty straightforward manner. We are using triangles inequality to do it. We simplified it, made it look like this. Z0 is minus B by A minus C by A Z0. Applied triangles inequality and did case 2. Right? That leads to the result. Okay. Let's look at the next problem. Let U be a root of x square minus x plus 2 is equal to 0. Let m and n be positive integers such that u square plus 1 whole to the power m is equal to u square minus 1 whole to the power n. We need to prove that m is equal to 3n. Okay. So since u is a root of this equation, we can immediately find the roots of that equation. By quadratic formula, the roots are half plus minus root 7 by 2i. These are the roots. So without loss of generality, we can say u will take it as the positive root, half plus root 7 by 2i. Okay. Now, u square plus 1, that's u is a root. So we have u square minus u plus 2 is 0. So u square plus 1 is clearly u minus 1. Right? So also, what is u square minus 1? U square minus 1 would be u minus 3. Right? So this equation can be written as u minus 1 power n is equal to u minus 3 power n. Right? And if we simplify this now, using the value of our u minus 1 would become minus half plus root 7 by 2 I cap power n is equal to u minus 3 would become minus 5 by 2 plus root 7 by 2 I power n. Right? This is what we are getting. And what we can do in order to find the relation between m and n, I can take modulus on both sides here. If I take modulus on both sides, the modulus of this is basically 1 by 4 plus 7 by 4, so 8 by 4, so root 2. So it is we are getting root 2 power n. Now on the other side, we are getting 25 by 4 plus 7 by 4, which is 32 by 4 or 8. We are getting root 8 basically power n, right? So that is equal to root 2 power 3n. That implies that m must be equal to 3. So this is a pretty straightforward evaluation type of question. What we did was we calculated the roots of the equation. We said that let's say that u is the root and u was half plus root 7 by 2i. And then we calculated u square plus 1 as u minus 1 and u square minus 1 as u minus 3. Put it as complex number equation and took modulus on both sides to get our final answer. Right, let's look at the next problem. Here have question which says factor 6 times a square plus b square plus c square plus 13ab plus 15bc plus 20cu. Question is strange because we are being asked to do a factorization. Now, there is no direct formula that will immediately give you this. So we'll approach it by the same method that we saw previously in the question where we had two parameters m and x. We can rethink the expression as a quadratic. So right now we can think of it as a quadratic in A or B or C. So right now we'll think of it as a quadratic in A and write it like this: 6a square plus a common, you have 13b plus 20c times a, and the remaining terms are 6b square plus 6c square plus 15bc. This is the constant term, right? This is a quadratic in A. So what we need to do is we find the roots of the quadratic, and write it as product of factors a minus a1 times a minus a2. If the roots are a1 and a2, the quadratic can always be written as product of factors, right? In this case, since it's not a monic polynomial, we have to write it 6 times a minus a1 into a minus a2, right? So all we have to do now is find the discriminant and solve this quadratic. So if you do the calculations, the discriminant comes out to be 13b plus 20c whole square minus 4 into 6 into 6b square plus 6c square plus 15bc. If you calculate this out, you will realize that this will come out to be 5b plus 16c whole square. So if discriminant is coming as a nice perfect square, the first root will be basically 1 by 12 minus of 13b plus 20c plus 5b plus 16c, which evaluates out to be minus of 2b plus c by 3. And the second root will be 1 by 12 minus of 13b plus 20c minus 5b plus 16c, which comes out to be minus of 3b plus 6c by 2. These are the two roots of the quadratic when you look at it as a quadratic in A. So now the factorization is obvious. We'll write it like this. On the next screen, I will write the factorization. It is 6 times a minus a1 times a minus a2, which is 6 times a minus, basically a1 was minus 2b, so it is 2b plus c by 3 and a minus, so it is plus 3b plus 6c by 2. And this will come out to be 3a plus 2b plus c times 2a plus 3b plus 6c. We have succeeded in factorizing the problem, right? So this is a nice trick again. We have seen this before. Think of the whole expression as a quadratic in one of the variables. Then solve it. And then once you solve the quadratic, you can write it as a product of factors. And that gives us the factorization. Okay. Let's go to the next problem. That will be question number 15. Here we have let A, B, C be non-zero real numbers. Non-zero real numbers such that 4 times a square by bc plus b square by ca plus c square by ab minus bc by a square plus ca by b square plus ab by c square is greater than equal to 63 by 4. We have to prove that at least one of the equations the equations are given by ax squared plus bx plus c equals 0, bx squared plus cx plus a equals 0, and cx squared plus ax plus b equals 0. At least one of the equation has real roots. Okay, so if you think about it, you can write the discriminant of each of these equations, right? The discriminant delta 1 will be b square minus 4ac. Delta 2 will be c square minus 4ab. This is b. And delta 3 will be a square minus 4bc. Right? Now, once we know the deltas, let's write the product delta 1 into delta 2 into delta 3. That is equal to b square minus 4ac times c square minus 4ab times a square minus 4bc. Right? Now, if you actually multiply this out, you will realize basically we have to prove that this is greater than 0. If the product of the determinants is greater than 0, you will be able to say that at least one of them has to be positive. All cannot be negative, right? Because if all of them are negative, product cannot be positive. So I need to show that this product is greater than 0. I have this condition, right? So let's simplify this condition here a little bit. I will do it on the next screen. I have 4 times a cube plus b cube plus c cube by abc minus I have b cube c cube plus c cube a cube plus a cube b cube by a square b square c square is greater than equal to 63 by 4. This is the condition that I have, right? So simplifying it further, I will get 4 times ABC times a cube plus b cube plus c cube minus b cube c cube minus plus c cube a cube plus a cube b cube divided by a square b square c square. So that goes on the other side. 63 a square b square c square by 4. You get 16 abc a cube plus b cube plus c cube minus 4 times b cube c cube plus c cube a cube plus a cube b cube is greater than equal to 63 a square b square c square. This is what I am getting from the initial condition itself. Now you will realize that if I bring this negative thing on this side, I will get minus 63 a square b square c square plus 16 abc a cube plus b cube plus c cube and minus 4 a b cube c cube plus c cube a cube plus a cube b cube is greater than equal to 0. This condition is coming from the initial statement in the problem, and you can easily show that the product of the discriminants is actually equal to this expression. The left hand side here, find the product of the discriminants, you will be able to prove that that is equal to the left hand side, which means that it is greater than 0, which means that one of the discriminants must be positive, and therefore the question is done. One of the quadratic equations must have a real root. That has been achieved. Okay, let's move on to the next problem. This problem we have find all polynomials of degree 2, polynomials of degree 2, where px is equal to alpha x square minus beta x plus delta, when alpha and beta are its roots and delta is the discriminant of px is equal to 0. So strange type of question. You have to find quadratic such that alpha, beta and delta come as coefficients of that quadratic, where alpha, beta are the roots and delta is the discriminant. Right? So basically the condition here becomes alpha plus beta, sum of the roots is equal to minus of b by a, so beta by alpha, right? And also alpha times beta, product of the roots is delta by alpha, right? And delta is equal to beta square minus 4 alpha delta, right? So we can eliminate delta because clearly from this we are easily getting alpha is not equal to 0 and beta should also not be equal to 0. So they are the roots. 0 cannot be a root. Because if 0 is a root, product of the roots is 0. That means delta is 0. If delta is 0, the roots will be equal and then alpha will be 0, which makes it undefined. So alpha and beta are both non-zero, right? And we can say that here alpha square beta is equal to delta and delta is equal to beta square minus 4 alpha times alpha square beta. We are getting alpha square beta is equal to beta square minus 4 alpha cube beta, right? Which gives us, we can cancel one beta because beta is not equal to 0, which gives us beta is equal to 4 alpha cube plus alpha square, right? Now we substitute that in this equation, we get alpha plus 4 alpha cube plus alpha square is equal to beta by alpha, which is 4 alpha square plus alpha. So one alpha gets cancelled. You have basically alpha square can also get cancelled. You have 4 alpha plus 1 is equal to 4. right? So 4 alpha is equal to 3. So alpha is 3 by 4. If alpha is 3 by 4, beta value can be gotten by putting it in this. To get beta is equal to 9 by 4. Alpha and beta are this. Delta would be 4 alpha cube beta. Delta is alpha square beta. So delta is 81 by 64. And the quadratic function, this weird function, is dx is equal to basically 3 by 4 x squared minus 9 by 4 x plus 81 by 64. This is a quadratic where the roots are also present. 3 by 4, 9 by 4 are the roots, and discriminant is also present as the coefficient. Okay, let's move on to the next problem. This is question number 17. Okay. We have let A, B, C, D, and E be real such that PAC is equal to B plus D and P belongs to minus half to half. Prove that at least one of the equations. The equations are given by x squared plus ax plus b equals 0 and x squared plus cx plus d equals 0. Prove that at least one of the equations has real roots. Okay. So what is the discriminant of the first equation? Discriminant of the first one is a squared minus 4b. And d2, discriminant of the second one is c squared minus 4d. We will work with this d1 and d2. Okay. So let's calculate what is d1 plus d2. 1 plus d2 is equal to a square plus c square minus 4 times b plus d. And we are given that b plus d is PAC. So this is coming out to be a square plus c square minus 4 times p times AC. Right? Great. So that can be written as, if you add and subtract a 4 p square c square term here, you will be able to make it a perfect square. We are doing completing the square method by adding and subtracting a 4 p square c square term, c square minus 4 p square c square. Okay. So if you complete the square like this, you get a minus 2pc whole square plus c square common 1 minus 4p square. So notice what has happened here. We got this as d1 plus d2. We wrote it as a perfect square plus something like this, right? And it is obvious that p belongs to minus half to half. So 1 minus 4p square is going to be positive. P modulus of p is less than half. So p square is less than 1 by 4. So this part is positive. This term is positive. This term is anyway positive. So we are getting d1 plus d2 is greater than 0. Right? Greater than equal to 0 possible. Both could be 0. Now, this means that both d1 and d2 must be greater than 0. Or at least one of them must be greater than 0. Or d2 is greater than 0. Why? Because both cannot be negative, because then the sum will be negative. So one of them has to be positive. If one of them has to be positive, then one of the equations has real roots, right? So as long as your P lies in this range and PAC is equal to B plus D, one of these equation has to have real roots, right? We have established that very quickly by taking the sum of P1 plus D2, right? Okay, let's look at the next problem. Let a, b, c be integers. Let a, b, c be integers such that a square minus 4b is equal to c square. Prove that the number a square minus 2b can be written as the sum of two perfect squares. Okay. ABC are integers such that this is true. You have to show that the number a square minus 2b can be written as the sum of two perfect squares. Okay. Let's look at the equation. Consider the equation x square minus ax plus b equals 0. The discriminant of this equation is a square minus 4b, the del of this equation. Now we know that a square minus 4b is equal to c square. So therefore the equation will have solutions x is equal to a plus minus c by 2. Right? So basically one root is x1 which is a plus c by 2. The other root is x2 which is a minus c by 2. So what follows from here is that product of the roots x1 x2 will be a square minus c square by 4. Right? And that means ABC was integer and the discriminant was a perfect square, so it could have a rational root. Basically, product of the roots is coming out to be this, and product of the roots from here is coming out to be what? It is b by 1 is a square minus c square by 4. Have I made some mistake? Like this correct? You are getting right. 4b is a square minus c square. Right, that is correct. So a square minus c square, if you think of a square minus c square, right, from this relation itself, you know a square minus c square is equal to 4 times b. And ABC are integers, so a square minus c square is even. Because 4 times b, right? So a square minus c square must be even. If a square minus c square is even, then both a square and c square have the same parity. Even minus even is even, odd minus odd is also even. So a square and c square have same parity. By parity I mean even odd. Okay. So if a square and c square have same parity, that implies a and c have same parity. So a and c have same parity that we have established right now. And if a and c have same parity, then x1 and x2 will be integers, because if you have same parity, then the sum will be even and the difference will also be even. So it will be divisible by 2. We get that x1, x2 are integers. Right? And if x1 and x2 are integers, then obviously x1 square plus x2 square, which is equal to x1 plus x2 whole square minus 2x1 x2, which is equal to, what was x1 plus x2 whole, x1 plus x2 was a, so this is a square, x1, x2 was b, so x square minus 2b, this is also an integer. We have established that x1 and x2 are integers, and therefore the sum of squares of x1 and x2, which is a square minus 2b, is also an integer. So a tricky solution here, we had ABC are integers and a square minus 4b is c square. We looked at the quadratic equation x square minus ax plus b because the discriminant of that is a square minus 4b. That was c square. So we got the roots of that quadratic pretty simply. The roots are a plus c by 2 and a minus c by 2. From the relation a square minus 4b is c square, we know that a square minus c square is even, which means a square and c square are both odd or both even. And if both of them have the same parity, a square and c square, then a and c have the same parity, which implies that x1 and x2 are both integers because x1 and x2 are a plus c by 2 and a minus c by 2. And if x1 and x2 are integers, then obviously x1 square plus x2 square is also an integer. And if you evaluate x1 square plus x2 square, that comes out to be a square minus 2b. Right? So a nice and tricky solution here. Now, what I want to do is pause at this stage. I still have around 5-6 questions that I want to show you, but this video is almost approaching 2 hours now. So what I will do is I will split the video, and part 2 of the video will have the remaining 5 to 6 problems that I wanted to show you. I will try and release that tomorrow. So that will complete our discussion of all types of quadratic equation situations, and hopefully it will prepare you well for any Olympiads or maths paper for JEE Advanced. So hopefully you have learned something from this video. The best way to go through these problem solving sessions is solving them yourself, pausing the video and solving it yourself. So hopefully you've done that, and I'll see you next time with the part 2 for this video, which will have the rest of the problems that I wanted to show you. So that's all for this one. See you next time.